Thank you for attending today. I'm Shogo Takada from the University of Tokyo, and I'll present our work on using smartphones to improve disaster search and rescue. In earthquake disasters, a rapid search for victims and a rubble is significant. In contrast to the conventional method that detects victims' voices, we propose a method using victims' smartphones. Here is our system overview. Our rescuer emits the sound waves created by dipole sound sources, which are received by a microphone in the victim's smartphone. And then, the victim's position is estimated and is sent back from the smartphone to the rescuer using Wi-Fi. Here is a fundamental localization principle using dipole sound sources. When two speakers on the x-axis around the origin are driven by sinusoidal waves at the same frequency in opposite phase, the sound pressure becomes maximum on the x-axis, but is cancelled out and becomes zero on the y-axis. In fact, the sound pressure measured by a smartphone at an RMS of phi is proportional to cosine phi. Similarly, if we drive another dipole sound source along the y-axis with the frequency different from that of the x-dipole, the sound pressure measured by our smartphone is proportional to sine phi. Hence, if our smartphone measures two dipole sounds, simply taking their ratio gives the RMS information. This is the basic principle. Here is a demonstration. We have four speakers composed of the x-dipole and y-dipole. They emit sound waves which are received by a smartphone in this black rubber tube in this experiment. Then the RMS angle is estimated in the smartphone, sent back via Wi-Fi, and it's shown on the rescuer's PC. Then the rescuer moves along the direction with the dipole speakers. Although the directions vary due to the refraction, we can approach the smartphone. When we come to the entrance of the tube, the estimate RMS turns to the right angle to the proceeding direction, showing the true smartphone's direction. This shows the estimated angle error while a rescuer is searching for a smartphone, which results in a zigzag path and delayed rescue activities. Therefore, we have to consider some refractions. So we consider adding one monopole to the two dipoles for the purpose of mitigating the effect of the reflected waves, which arrive later than the direct wave. Here are the two steps we perform for a more accurate RMS estimate. First is to identify the direct wave from reflected waves using one monopole. Second is to extract direct wave components from two dipoles which contain the genuine directional information of the smartphone. This slide shows the experiments conducted to validate our method. At labo site, within 10 by 10 meters, the smartphone was placed at 14 locations shown by the yellow circles. The light figure illustrates the estimation performance at 14 locations. In short, all three error criteria decreased in our method, compared to the other conventional approaches, enabling a more accurate search. Thank you very much for your attention.
All right, we know the drill by now. We'll do some question and answer. So I'll ask Shogo Takada to please come on camera and we will spotlight you.
Hi.
Hello. Okay, hold on. There we go. All right.
All right, thank you so much. That was this is so interesting um, and innovative. We were excited to read all about this as we were working on the materials for the press conference, and we have a couple questions in the Q&A. Um, the first one is from Richard, and he's asking, "What does the victim have to do to make this work?"
Okay, I think the next question is the same. Yes, we expect that victim install the app for the localization in our app research and in advance. So yeah, only installing the app for the localization, the victims does not need to any other uh, command in disaster research, disaster environments.
Gotcha. So they just need to have the app on their phone.
Yes, correct.
And that answered our second question from Avery, as you mentioned, and then we have a follow-up from Richard asking, does it require Wi-Fi? Um, and if so, how far under a rubble pile, would you think that would work?
Yes. Firstly, yes, we expect local Wi-Fi is used for sending the results of the azimuth angle calculated by a smartphone, and it is not the same as a radio wave. So local Wi-Fi can be used if rescuers just have a Wi-Fi router in the near place. Yeah.
I got you. And then the phone would need to be turned on. That's another follow-up question from Richard.
Yes, it's a tough questions. Yeah, of course, the smartphone have to be uh, have the turned on. So, but the app in the localization is uh, not so uh, tough calculations. It's only the calculates as I mentioned in the videos, the azimuth angle for the uh, brief calculations. So the app is not consume the batteries in smartphone.
I got you. And then um, the last question we have in the chat, this one's from Maya, is can a slightly damaged phone still be used in this method?
Yeah, it may happen in real disaster environments. The smartphone plays an important role in our system. It receives the sound pressure and estimates the azimuth angle. Of course, if the device is broken, our system can't work correctly. But as long as microphone and the app in the smartphone can still work, our system can help localize and search for the victims.
That makes sense. And one more question from Richard in the chat is, how big would a real world locator be?
Uh, Now, in these experiments, the range of the localization is just 10 by 10 meters squares. But in our future work, we plan to extend our localization range like 100 by 100-meter area by using drones with speakers flying around the disaster site. Locally, we can estimate the smartphone position within a 10 by 10 meter region, and we can cover much larger areas in total.
I got you. And I think I think what Richard was talking about is the device used, so the device that emits the sound, about how big is that?
Sorry, which is a question?
Um, so the emitter, how big is that device?
Biggest.
The size?
Deviceのサイズ。
Ah, the size is just you you think of just a smartphone. Speaker size is just uh 26 centimeters by 15 centimeters. We use four speakers.
So those would just be put onto, say, the drone, and then that would help. So they're small enough to be put on like a drone.
Yes, speakers are small enough to carry in drones.
Let's see. Anna Shay has a question in the chat. She's asking if there are multiple people in a small area, like in an earthquake, is interference among different devices a concern at all?
Yes, it's like essential information. Yes, yes, each smartphone has a unique ID in Wi-Fi communication. So simply it is possible to distinguish which device lies in which direction.
That makes sense. All right, so I guess Richard just wanted us to confirm, so is the devices emitting the sound, is it like an array of drones that would be over the disaster area?
Drones array?
Yeah, I think if you want to look, it's the second to last question from Richard. But is it like an array of drones that carry the speakers that then are used over the disaster area?
Yes, at this moment, we expect that an array of drones is like the in videos for speakers.
All right.